Hey everybody, so I'm going to do our notes today for day one, describing motion, in our new unit, Unit 8. So if you can follow along, got a lot of notes to do for the first day, and a lot of it's going to be a review, but we're looking at just being able to describe what rotational motion is and using that information to kind of approach these types of problems. So let's look at the, oops, I am too far ahead. Hold on a second. Let's go back to the beginning. Okay. So one of the things that I want you to recognize is that our energy is pretty much the same as our linear motion. All the constants and variables can be transferred over. So for whatever equation you have for linear motion, you also have those for rotational motion as well. One of the key things that you should define before you get started is what angular position is compared to normal position. We're measuring that in theta, or angle. And then velocity is angular velocity, acceleration is angular acceleration. Now, if you remember those key points, then you'll be well on your way to understanding what is going on in rotational systems. You can see up here, I wrote the equations out for linear in red at the top, and then we have rotational in green here below. So they are related in that they are the same, they just have different, variables and amounts that go together. All right, so will this work? Probably. Yeah. So one of the interesting parts about this is the force that is at play in a rotational system. You can see here that we have a wind turbine that has failed. The brakes sometimes fail on these, and they get rotating to the point where the acceleration is too great, the forces are too strong, and the blades fail. That one you can see karate chopped its own stem. And you'll notice all the blades failed at once, which, for design of the wind turbine, they have a certain threshold that they should be operating at. And a tornado is not a good operating system. The brakes should be applied in wind conditions such as this one. Of course, brakes aren't going to help if it just breaks it apart due to the sheer force of the wind energy. You can see parts of it flying off into the distance. Very expensive to fix or repair. Something that's blown apart by a tornado. You can see the aftermath here in a moment. We try to put these in high wind areas, so it makes a lot of sense that you might end up with tornado effects for those places. Oh, this is just unfortunate. If you like birds, then you probably don't want to watch this. It's fine. It's fine. It's huge, by the way. I don't know if you can. Oh yeah, there's a close-up. Oh yeah. So this is on purpose. If I remember right, these were not built correctly. They didn't have a good foundation. It's pretty hard to actually visualize how big that is. You know, they are gigantic. So, but you can see the base did fail. They didn't have enough counter pressure there. This is showing a lot of the forces going on. The towers move a ton. So you can see the flexing of the metal base. The brakes were applied. This is the inside shot. They have a chaseway so you can climb up and down, where they can run all the cables. Oh, look at that. That was quite a gust. You don't really want that to happen. So the brakes were applied, but I mean, it's still in the wind. Quite a climb, though, right? To get up there. Quite a climb. People do this for a job where they get up there, service them. The Bancrofts have a pretty nice crane that they use to do that. This is most likely overheating of the brakes. You can see that there's a mechanical failure with the generator, or the brakes were overheated and lit some of the flammable material inside on fire. But once something like this gets started, there's really no way to stop it unless you were able to drop a helicopter load of water on top of the wind turbine. So that doesn't really have much to do with rotational energy, but you know, pretty dramatic. And there is a possibility that we could be servicing something like this and get stuck up there. That's happened before, and it's pretty awful. So, all right, so what are we looking at for our measurements? Well, in terms of the motion of something, we need to describe it as a, displacement, basically. So if you have a displacement of something that's rotating, the easiest way to look at it is from the perspective of angle. So it's an angular position, which we measure in theta. So we're essentially measuring arc length for the motion of particles in a circular pathway. So that's measured in radians, not degrees. So in mathematics, you'll notice it's actually the same way if you're doing trigonometry. Sorry, Quinn. But in the measurement that we're looking at this from the center of the circular motion. We're measuring the rad, or the radians. Rad, dude. So the arc length and radians. So how do we define that? Well, we define the particle's angle in terms of the arc of the radius of the circle. So the theta in radians is equal to S over R, and the S over R is the radius and arc length. Now, as you know, hopefully, that one complete revolution is 2 pi rad. So 2 pi r over r is a full circumference, a full circle, one revolution. All right, now we have certain understandings from our linear motion where we talked about how displacement, larger displacement, equates to a faster speed. If I move fast, I'm going to be covering more delta x for a certain amount of time. This is a very common way to show these problems as like a snapshot, where after a second, oh, look, you're here, and then you're here, then you're here. And this over here would be, you know, Cecilia race walking. Not really, this would be Cecilia race walking here. Same goes with angular displacement. So if you have an angular displacement, you're going to be covering more radians, more, you know, degrees in the same amount of time. So if you have, you know, like a wheel, and the wheel is rotating at a slow pace versus if you really got it cranking, you know, and the wheel is moving faster, it's a singular point on this is going to cover much more area in a second's worth of time. So it's a measure to how fast it's going. We had a hill that we used to come down. It was part of my grandfather's property. And at the bottom, there was this really steep turn that you took right before you got to the road. And we used to kick dust up like crazy when we were biking down this hill. So we came down and, you know, we're negotiating the turn. We're going really fast. But on this day, it was particularly dusty, and the trail usually has a little better traction, but it was so loose that the corner was really hard to negotiate. So we're going really quickly, trying to make this turn. Had a lot of, you know, velocity coming into it, but now it's going to be angular velocity. And my friend Beefer, you know, the big kid, he didn't have quite enough traction for that amount of force trying to make that angular displacement. So instead he went into the woods and avoided the trees, but his angular velocity was not maintainable with that amount of traction. So what we're looking at for describing that velocity is just how much you're having change over your time interval. Okay, so that's this one right here. Your angular velocity is equal to the change in your radians over time. Okay, so if we were to look at these two particles, we have in the first motion, you can see we have a particle with a small angular velocity, and it's undergoing a small angular displacement for each second. And then you have a larger displacement for the same time interval. Hopefully you can see that one particle moves half of the circle in the same amount of time that it takes the other one to only move a quarter of the circle. So the displacement of one is essentially double the other. So one radian is 60 degrees, and the particle on the right is moving at about the same period across its whole motion. So it's going to be moving, you know, at a slower angular velocity according to our calculations. So they are moving, we have the time frame in seconds. They're each moving for 5 seconds. So if we make a comparison between the particle on the left, we can see that it's moving pi over 2 radians for 5 seconds because it's moving a quarter of the circle. That means it's moving at 0.314 radians per second, as you can see there. Whereas the particle to the right is traveling around half of a circle, or pi radian, meaning that its angular velocity is going to be pi radian over 5 seconds, giving you a angular velocity of 0.628 radians per second. So that's the kind of speed that Beefer wouldn't be able to maintain without flopping into the woods. So just kind of pulling that whole idea together, you know, you can see that the speed is roughly double, which should make a little bit of sense as far as comparison's sake is concerned. So, and you can convert between the two systems. You know, obviously, if you're moving in a straight line, then you're going to be measuring your just regular velocity. And the speed is still tied up with time. Like, we're still looking at the change of time. It's just the displacement's a little bit different. So to convert from one to the other, you have to take it out of rotational and into linear. Another thing, and this applies to the unit we just finished rather hurriedly, is the idea of frequencies. So you can also measure the angular speed because it is a rotating system, which might follow the simple harmonic motion type of stuff, you know, where it travels around and comes back to where it was. That is simple harmonic motion. So you can look at the frequency instead of the just using time. So you can use frequency to calculate your angular speed, which could be helpful with some measurements. All right, so we have a ball rolling around a circular track. It's got an angular velocity of 4 pi radians per second. What is the period of that motion? This is what I'd ask you, and you'd be like, oh, man, I don't know. But if you think about what they're saying is they want to know the period, but they're telling us the angular velocity, right? So the angular velocity is 4 pi radians per second. So if you remember from the previous slide, if we know what the frequency is and we know the angular velocity, then you can, you know, use that to find the period, because the relationship between frequency and period is always inverse, right? So in this case, since it's 4 pi radians, how far around is that? Around a circle, right? What's one circle? This is weird when you're not here. One circle? That's right. It's 2 pi radians. Good job. Good job. Yes. Empty room. Yes, I think you're right. Wow, it is 1/2 s. That's amazing. Good job. Because the period is 2 pi over your angular velocity, because it's an inverse relationship there. So way to go, fake students. Well, you're real students. You're fake. You're fake to me. I mean, you're real. You're real. Like, I miss you and things. But like right now, you're not here, and it's sad because I'm by myself with my moles. Okay, so let's say you're driving your, let's see, your Subaru, whatever the heck Isabel drives, or your Toyota Sequoia Sienna or whatever Sam drives. But anyway, so you're ripping along at 3,000 RPM. What is the shaft's angular speed? All right, so in calculating this is a very similar, not similar. This is a very common, I guess you could say, measurement, right? RPM, revolutions per minute. If you get the chance to ever drive a standard, then you'd, be looking at this all the time, because that's, you want to kind of time out when you want to shift your vehicle to make sure that you don't rev your engine too high, which could cause some damage. That's a lot of damage. Don't want to do that. So let's work this problem out on the old whiteboard over here. So you're driving along. My art has improved. So you're driving along, your engine's going at 3,000 revolutions per minute. I had to think about that. So RPM, revolutions per minute. All right, so weird unit, right? we don't usually measure things in minutes. We like to measure things in seconds. But unfortunately, we all know that there's 60 seconds in a minute, right? Give it a minute. So we're going to take 3,000. I'm doing this on a calculator. That's divided by 60. That's 50. So we're going at 50 revolutions per second. That sounds like quite a bit. That's faster than I could pedal a bike for sure. How do we find the angular speed from that? Well, that is in fact a measure of frequency. Okay, that's the same thing as hertz. Okay, that rotational motion is the same thing as hertz. It's measuring how many times the engine cycles around, per second. So it's doing it 50 times per second. So you might want to shift, especially if it's a diesel. All right, so we can calculate our angular speed knowing that this is in fact our frequency, knowing that 2 pi radians times your frequency is equal to your angular momentum. Okay, so let's put our number in there. So we have 2 pi radians, and we're multiplying that by 50 to get our radian. We need it to be in radians per second. Okay, so multiply by 2 pi, and we get 314. 314.12. So 314 is close enough. Okay, so what's going on with our units here? I left revolutions off of there, but this is basically hertz, which means that you're going to have radians in there, and this is per second. It's 50 revolutions per second. Revolutions is gone. It's just per second, so it's radians per second, and that's a normal unit. For rotational systems, angular velocity would be measured in that way. So that's pretty. Yep. That's how that works. All right. So check my answer. Oh yeah. Okay. So angular position and angular velocity graphs. So in looking at the motion of something, if it's uniform, it's going the same speed the whole time, then a velocity versus time graph wouldn't be super helpful. But if it's speeding up, an angular velocity versus time graph would be great. Position versus time graph can help you calculate the angular velocity of objects, which for something speeding up is really helpful, so you can tell what its angular acceleration is, and then you can measure your change in acceleration if it's undergoing some other outside force. So to translate from one system to another, here's our tie-in, is that you need to know your angular speed. Let's say you know your angular speed, but you also need to know where it is on the circle, so you need to know your radius. And this is really kind of key for the idea of merry-go-rounds. Like if you're circling around a merry-go-round, you can perceive speed being different, but the weird thing is that the angular speed is the same. Okay, so that's kind of a weird idea because if you're sitting on top of this compact disc, CD, that's what CD stands for, it would absolutely feel a lot different at position B than A. I hate spinny rides, so I would be sitting as close to the center as I could so that I don't get sick. My kids love them for some reason, and they make me go on them until I can't see straight and feel like I'm going to throw up my doughboy. But, you know, I'm the best dad ever. So, of course, I'm going to go on the spinning teacups up a zillion times. So, and the reality of it is that the angular speed is the same. So here we have a CD, and it's going to spin around at 540 RPM. There's the 540 RPM, yeah. The revolutions per minute. Is that it? That's not much. What is the speed of point A at a distance of 3 centimeters from the center and B to the outside of the edge? Okay, I gotta draw this real quick. Circles, and I can do circles. So we have point A and then point B. It's rotating this way. It's probably playing Mole songs. I mean, what else would you really listen to? And the first position is 3 centimeters out. And then the second position is 6 centimeters out. That must be on the outside edge. I don't think they're much bigger than that. So what are we trying to find? We're trying to find the maximum speed for those 2 points. Okay, so let's see if we can figure that out. Now you can see my drawing really good. It's really good drawing. So we have revolutions per minute. We just did a calculation with revolutions per minute. We need to see what it is per second. So we're going, I thought CD spun a lot faster than that. So we have, again, 1 minute. We want minutes to cancel out. 60 seconds here on the bottom. So 540 divided by 60. 9. Ah, there's no way that's how fast the CD rotates. All right, so we're at 9 rotations per second. Sorry, revolutions per second. So again, that's a frequency calculation. So we can calculate our angular speed for that, meaning that we have to do 2 pi radians. Radians, again, is just our unit times our frequency, f. So 2 pi radians multiplied by 9, and that's per second. So 1 over seconds. It looks like 1/2, but it's not. It's inverse seconds. Maybe if we do like seconds to the -1. Does that help? So we're doing 2 pi. Oh man, I haven't had pi in a really long time. 2 pi times 9 is 56.5. 56.5. So W, it's not a W. I shouldn't call it a W, but I'm forgetting what it is in Greek, Latin right now. 56.5, and that is radians per second. Okay, so that's how many radians per second the disk is rotating. But that's for the whole disk. That is not for those particular positions. We want to know the velocity, the regular linear velocity for those 2 positions. So we're gonna move out of one system of measurement into the other one. So it's a little weird. So let's look at VA first. Now, if you remember, the equation that we looked at was just whatever your angular velocity is times r, its position on the rotating system. So we had, for both of these, it's moving at 56.5 radians per second. And then we're going to multiply that by A's position, which is at 3 centimeters. Gosh dang it, it's 3 centimeters. So that's 3 divided by 100. That means it's 0.03 meters. It had to be in meters. Everything has to be in meters. It's physics world. So times 56.5, and that's 1.7. 1.7. That's meters per second. Meters per second. Okay. 1.7 meters per second. Now let's look at B. B is at position, it's at 6 centimeters. So, but they still have the same angular velocity. It's just one of them is a little further out. So it's 0.06 instead of 0.03. But it's still 56.5 times 0.06. So we're looking at 3.4. Oh, it's double. I'm stupid. All right, so 3.4 meters per second. So that's why I ride on the inside of the twilty wheels. That's not a thing. Or the, what is it, gravitron? Oh, wait, you can't ride in the middle of that. Actually, that's where the operator sits, right? Operator sits in the middle of the gravitron at the fair, right? And then we sit on the outside edge and get stuck to the wall. And that's because on the outside edge, your acceleration to make that turn has to be much, much faster than if you're closer to the middle. So the operator doesn't feel any force because he's like right in the middle of that rotating system. All right. So did we get those right? Yep, okay. All right, so here's a graph showing a wheel similar to this one, rotating around, and it's showing your revolutions per second and your time on the other side. You can see we do have an increase in your revolutions per second. So how many revolutions does the wheel make in the first 4 seconds? So you got to think about what that means. In 4 seconds time, how many revolutions does it make? You can see at 4 seconds, it's making 2 complete revolutions per second. So you can kind of make a guesstimate answer pretty quickly. And you were right. Of course you were right. So it's 6. If you, I'm pointing at it. Oh wait, let me use the mouse. So 1 plus, well, a half plus a half is 1, plus 1 is 2, 3, 4, 5, 6. It's the area under the curve. Calculus, kids. Yeah, area under the curve. You love that. Okay, so I gotta stop talking. So starting from rest, a wheel with a constant angular acceleration turns through an angle of 25 radians in time t. What would the angle, what angle will have turned after 2t? So double the time. So we went through, this is angular, constant angular acceleration. Okay, so in the first time, it was 25 in time t. So what if it's double time? You might expect it would be double the distance, right? But it's under constant angular acceleration. So it can't just be 50, it's got to be more than that. So if it's increasing in its acceleration, well, constant acceleration, sorry, increasing in its speed after double the time, then we're looking at 100 radians per second, because the amount of time basically is squared. So it's roughly equivalent to the amount of time squared. So you might expect it to be 50 if you thought maybe it was just double the time, so it's going to go double the distance. But because it's accelerating the whole time, it's actually equal to the square of that. All right, so rigid body. Who's with me? So rigid body is the extent, the object in physics world. Remember, we have weightless strings, right? We have no friction. What else do we have? Oh, no frictionless pulleys is another one. Oh, there's a lot of weird things. But one of the things is that these structures we're rotating cannot flex and are perfectly rigid. We know that's not the case, right? But in physics world, it is. One of my favorite biking stories was they had these rims that came out. They were called Spinergy wheels. Maybe I can find a picture. And the Spinergy wheels is, it was supposed to be like unbreakable, is what they said. And they were just the wackiest looking wheels ever. And, you know, they said, oh, you know, you could jump your bike off of a cliff and you would, you know, the bike would be completely wrecked. So you'd be dead, of course, but your Spinergy wheels would still be, you know, intact. I can't spell. Let's look at the images. So these were the road versions. Oh, here they are. Yeah. This was the coolest thing you could get on your bike. All right, so you were flexing really hard if you showed up to the, you know, the town bike ride with a set of these suckers on your bike. You'll notice that they have, it looks like 4 spokes when you first look at it, but they're actually doubled up. So you have for each wheel 8 spokes. They're very thin carbon fiber. This is the very beginning of the use of carbon fiber, and we were not good at it yet. So the idea was they were incredibly rigid. They kept their alignment. You know, a good wheel will be true. So, you know, if you rotate it, there's not any wobble to it. It stays in a nice straight line. That way your brakes, like, don't tap on the, you know, because if the wheel's all wobbly, then your rim brakes won't work very good. And these were rim brake wheels, so they had to be nice and straight. So the idea was that they're light, they're carbon fiber, they're excellent wheels. You can go super fast and have lots of friends. But the reality of it was that there's only 8 spokes on the wheel, whereas a normal wheel has 100, wait, not hundreds, 1, 2, 3, 4, 5, 6, you know, 56 spokes. And if you break one, right? If you break one on those, you're gonna die. So, and you're usually going as fast as humanly possible when one breaks, you know, so the stresses are really great on those wheels. So if you break one of these, the wheel goes all pattywampus, it hits your fork, it hits your frame, the whole thing just breaks all apart, and your body gets to meet the ground at a high rate of speed. So one of our show-off friends who had, oh, I gotta show you the bike. Oh my gosh, you're not even gonna, yeah, you probably don't even care actually. But come on, there it is. Oh gosh, so ugly. So they showed up with one of these bikes with those Spinergy spokes. Do they have one of the combo? Oh, that's it right there. Oh my gosh. Ugh. So he showed up with one of these. This was yellow though, but fun fact, these are also carbon fiber, but we're going down this hill at Colby College, right? So picture this. He's leading the group because he has the best bike. He can hit all the bumps the fastest, you know, so he's leading the way. This trail down from the water tower has a lot of these big bumps. Super fun to just kind of launch off and not even bunny hop. You're just going so fast, you just kind of take off from the ground and it's super great. Well, he gave it a little hop, came off the ground a long ways and landed really hard. This has front and back suspension, but the suspension back then wasn't made for something like that. And a lot of force went through the front wheel. Too much force because it broke two of the spokes and the wheel basically just exploded at that point. The fork sticks in the ground, the whole bike escapes from underneath him, and he gets to ride down the hill on his face. So, yeah, and he did not break the frame of the bike, but I mean, it was quite a awful crash. So, but in physics, the idea is that it won't do that, right? Like it's going to be a nice, solid, rotating system that is not going to deform or anything like that, which is a good system for us. And what's really interesting about that, and we'll expand on this idea next time when we talk about center of mass. But rotating systems, can be anything, right? So if I have this board and I rotate it, it's still, it's still rotating, and it follows that same idea where it's moving around a fixed point, right? It gets really complicated when it's doing both rotational and translational. That's basically trajectory, and that gets really complicated unless you know what center of mass is, which again, we'll be talking about that next class. But in a rigid body, what we're really describing is that every point moves at the same angular velocity, right? It's not like that Trek bike when the Spinergy wheel broke off one of the spokes and the whole thing went at different angular velocities, which is really bad. We're talking about everything traveling at the same angular velocity in that rotating system. So each point you identify are going to be moving at the same relative angular velocity. Okay, and they don't ever change. They're always moving at the same speed. So back to the merry-go-round idea. If you're on a merry-go-round, but you're in different positions, Sophia is going to be twice as far from the axis as Rashid, then the angular velocity comparatively is the same as, because they are on the same rotating system, and we're talking about angular velocity, not velocity, right? Or speed. So Quinn and Isabel, that's weird, the names change, huh? On a merry-go-round that's spinning steadily, and Isabel is twice as far from the axis as Quinn, so Isabel's speed twice as far is at half, the same as, twice, 4 times, or you gotta love option E, you can't say without knowing the radii, right? Although we do know it's twice as far, so it's twice the angular speed. We saw that in the compact disc example, that double the distance is double the speed, okay? All right, so you have coins on a turntable, and what is the angular velocity comparatively of those? Again, angular velocity means that they're moving at the same speed. So the angular velocity of A is equal to B because, again, they're rotating together on that same object. All right. Angular acceleration is the change in angular velocity over time. That shouldn't be too surprising. The units are radians per second squared, just like in a acceleration standpoint, it's meters per second squared, like gravitational acceleration and the like. They all are very similar that way. So if you have a system where you have a rigid body, right, accelerating from a standstill, and it's moving faster and faster and faster, like you're going down a hill at Colby College on your awesome mountain bike, the direction is a key part of that, right? Like on our number line, if you're moving in a positive direction versus a negative direction, you know, we define that in a certain way to kind of make it easier on ourselves. So the way we're going to work that with angular acceleration is that if it's going to be positive when you're rotating counterclockwise and speeding up, or if you're rotating clockwise and you're slowing down. It's going to be negative if you're rotating counterclockwise and slowing down, or rotating clockwise and speeding up. Okay, most of the time this isn't really a problem because we're just kind of describing the change in your acceleration, so it's not going to matter too much, but that is how they are defined in the positive and negative. So here we have a fan blade. It's spinning, you can see hopefully, in the clockwise direction. And the clockwise is slowing down. So you unplugged it or whatever, and it's coming to a stop. So they should align, right? Like it's the acceleration and your velocity are both being affected by the, by the speed, by the motor not pushing the blade anymore, so it's slowing down, okay? So in which case, your speed is going to be negative because it's decreasing. It was faster before and it's slower now. And because of its direction, the acceleration is going to be positive. Okay, now the blade is speeding up. Okay, so now it's plugged back in, and it's spinning the same direction, but it's moving faster and faster and faster. In which case they're aligned, right? Like the motor's helping it go faster, so it's accelerating quicker, and the speed is increasing, the angular velocity. So they're both going to be increasingly negative because of the direction it's moving. All right, just a quick table showing the relationship between all those parts. And all right, I want to skip ahead a little bit, but starting from rest, a wheel with a constant angular acceleration spins up to 25 RPM in time t. What is its angular velocity after 2t? So how do you describe that? Looking at the resulting acceleration, we're talking about 25 revolutions per minute, and that is from rest. So it went from 0 to 25 in time t. How fast should it be going after 2t? We had a question similar to this before, but the idea is that your time for angular velocity is going to be relatively proportional or equal to your change in time. So if you have double the time, it's double the angular velocity. Not so for velocity, right? Like linear velocity. We're talking about angular velocity with that one. That's because of the acceleration, right? So this is a carryover from before. We've talked about rotational systems a little bit, so we understand that the acceleration has to keep the object rotating by pulling it towards the center. Okay, so if we have a rotating system like this, the spokes here are actually responsible for holding the outside rim towards the center. If these spokes weren't here, then the wheel would, fly off to the side because of the forces of it rotating around. And they're tangential to the acceleration. So they always go towards the center. And it's proportional too. So if it's moving faster and faster and faster, then the acceleration has to be greater in order for it to continue to make the turn, which is why those windmills failed because most of them were moving past their capacity. So here's the relationship between acceleration and your rotating systems. We have our acceleration is equal to your change of velocity over time. Change of velocity, if you remember, was the change in your rotational velocity times r over t. So you can calculate it like that. And if you derive it out, really what that means is that your acceleration for a certain amount of time is equal to your rotational acceleration times r. So it's almost the same exact equation we saw earlier for velocity, which is really handy. So you can convert between the two systems and understand what's going on in those systems from linear to rotational speed. All right, so a couple other things that we need to talk about. Torque. So in the movement of a rotational object, you can't not talk about torque, because torque is what's making those things rotate. The fan motor applies a torque to get the fan to spin. If you're on a bicycle, your legs are gonna, have to pedal to make the bicycle move. If you're talking about a car, like your engine has to, put the torque in to get the tires to move, to get the rotation of the transmission to work and all those parts. Really simple idea. It's just force at a distance. So you can apply a ton of force, very close, fulcrum, or you can apply a little bit of force a long ways out. Okay, so if I had like a big stubborn rock or something that I was trying to move, you'd want your lever to be as long as you could get it so that you don't have to use a lot of energy. Like, it's a lot less force versus pushing it from a closer distance. The force is applied, has to be much greater to do the same amount of work. And it's a really straightforward measurement, because all you have to do is measure the radius of the lever that you're using and the amount of force that you're putting on it. Okay, for me, look at that. That's a lot of force. That's a lot of force. It comes out to Newton meters. This, before I savagely broke it, was 30 centimeters or whatever. But unlimited force, it stood no chance. But it would be measured in Newton meters. So the bigger the wrench, the more force, the more torque you can apply using the same amount of force. Now, some of these systems can be really complicated, so we use what's called the radial line, which is just a simplification of the tools, and the force is being applied, at some degrees off from that radial line. If you want to be the most effective, you want to be a perfect 90 degrees to that lever arm. Okay, that way you're transferring all of your energy to, the torque instead of having some component of it. Yeah, here comes some component stuff. Because if you're not applying the force perfectly perpendicular, then you have to figure out what amount of force is being applied. So you can see here in the diagram that, whoopsie-doo, because we're not applying the force perfectly perpendicular, some of the force is not really doing anything. It's actually trying to pull the wrench off of the nut, which is not going to be helpful. So yeah, you have to break that force down into the components, which we love to do because triangles are the most fun, right? So if you do have to do that, you can also take a shortcut and look at a fake lever arm. We call it the moment arm. And this is very common actually in design materials and manufacturing, because a lot of times you can't apply the torque exactly how you want it. So you have to calculate this imaginary moment arm, which would actually be applying the torque. It's still related to triangles. You can see it's got a right angle there, and your force is being applied to a fake moment arm, but it will be perpendicular to that moment arm, which makes the calculation maybe a little bit easier. As long as you know what your radius is, you know what your angle of attack is, then that will help you calculate the actual torque that's being applied on that tool. So if you have a measurement that follows that idea, it's still going to be force, right? The force that you're applying, but you're going to multiply it by the moment arm radius, which you can see is shown as a R with the little perpendicular sign next to it. Or for both methods, really, it's just R times F sine theta. That's not theta, but I don't remember what that one is either. Rotational stuff is weird. So if you're trying to close a door and you're smart, then which one of these would be the best way to close it? You can see the hinge. You got force 4 is close to the hinge. Force 3 is, far out from the hinge, but at an angle. Force 1 is far from the hinge, perpendicular. And force 2, who is force 2? Who is that? Is that the person that pushes on a pull door? Is that what's happening there? That's like that time in indoor track when somebody opened a door when we're running around the hallway and you got it like right across the face. That's force 2, right? So if you're smart, you're going to be force 1. Force 1 is perpendicular, a nice distance from the door. You're going to push that door and successfully enter the room. Just make sure they don't have coronavirus in there. So if you're trying to open, a door, but you only have so much energy, you can only push with 240 newtons. Oh man, how much torque can poor little Ryan exert, and how could he exert more force? Well, if he was smart, he probably could have exerted the force in a perpendicular way, but in the case of him pushing on the door, I guess he's not capable of doing that. Maybe there's somebody standing in the way or something like that. I'm not really sure. But let's just look at this example here real quick. All right, so we have a door that we're pushing on. Hinge over here. And we got, what was his name, Ryan? It's pushing this way for 240 newtons. And the door has a radius of 0.75 meters. Is R. Okay, he's not pushing at a, at the correct angle. The correct angle was 20 degrees off from the way he's pushing on it. So that's not super good. And so because he's pushing it at a weird angle, we have to make into account the the equation makes with the angle takes that into account. I'm just zipping back to the equation here. So the equation is the torque, which is a weird tau like T that does not look at all like it's supposed to. Oh, there we go. Torque is equal to the radius times your force sine of your angle. Okay, so our radius is 0.75 meters. Your force is 240. That's newtons. And your sine of 20 degrees. So what is our torque equal to? I don't know. That's what the question was. Let's find out. So we have 0.75 times 240 times sine of 20 is 61.56. All right, and that's Newton meters. Newton meters. Which, sounds pretty reasonable considering what is going on. For that position, and so that's quite a lot of torque, for trying to get, but the door is stuck. Like normally a door would just swing open really easily, but presumably it's stuck. So we got to push it harder. Did I do math wrong? Wait, why is my force wrong? Hold on. 0.75. Did I copy that down? Hold on. I must have made a math error somewhere. So 240 times sine 20. Oh, huh. Oh, it's cosine. Oh my gosh. Cosine 20. All right, so 0.75 times 240 times cosine of 20 is, yeah, 170. Okay. All right. I goofed that up. And Ryan could have done a much better job if he had pushed it, you know, at the very edge of the door, or you could push harder, I guess. So torque depends on both the radius and the direction that you're applying the force to. So you could apply the force in a positive direction or a negative direction. It follows the same positive and negative rationale that we talked about with the rotating systems. And in systems that are more complex, you end up with a lot of different forces being applied. So you have the, you know, the typical bicycle crank here. And if you're pushing on it to try to, you know, move forward and on the bicycle, there's a lot of forces being applied. So your foot is pushing down. The axle has to push back to keep the whole bike from falling apart. The wheel is connected through the chain. The chain sags underneath. You can see force 4. Maybe your other foot, force 2, is also pushing on the pedal because you're stupidly dumb. You should pull your foot up with the clipless pedals. You can do that. And we've been talking a lot about bikes today. But the idea is that there's a net torque that you can measure. For bikes, they have a torque meter that actually goes on the bike itself and can measure how much torque you're putting out. I don't use that because that's a road biker thing. And I'm a mountain biker. We don't care. We just jump off of stuff. So here we have a system. We have a pivot. We have a point P. And we're trying to just roughly guesstimate what kind of force we would need to apply at point P to basically get our net torque down to 0. All right, so we have our pivot. We have this other force here at the bottom. What would be the opposite of these two, but equal to these two? Which direction would it have to go in to cancel these out? If you make a triangle out of these, keeping track of what direction the arrows are going, then it might be pretty obvious that A would be the other end of that triangle. So triangles are key here in trying to figure out what the resulting would be for something like that. And yeah, so that's torque. That's rotational systems and defining rotating systems. And hopefully that was helpful for you. And I'll share some other resources to help you along your way. All right, see you guys later.